Okay, so we talked about a central force between two objects of mass m1 and m2 in the last problem. And we looked at, again, I wrote this in terms of big R. Let's again write it in terms of RCM. So that's the center of mass. So if we want to look at things in terms of coordinates that involve the center of mass, and then we have R1 and R2, right? The vectors pointing to the location of the two objects of mass m1 and m2, then we can treat this in the Lagrangian formalism, where we say that there's a kinetic energy, m1 plus m2, the total mass, and there's an R center of mass dot squared, and then we have m1 over 2 r1 dot squared plus m2 over 2 r2 dot squared, and then we have minus the central potential, which hasn't been specified. Of course, our center of mass, the velocity of the center of mass is equal to a constant, right? We saw that, so it really doesn't affect the equations of motion. And we could also choose the center of mass to be 0, in which case we end up with m1r1 plus m2r2 equals to 0, right? Because this our center of mass is this divided by the total mass. So if that's equal to 0, then that becomes 0. And then R is R2 minus, or R1 minus R2. The vector at R between these two involves the differences between R2 and R1. And this gives us R1 is equal to M2 over M1 plus M2 R, and R2 is equal to minus M1 over the sum of the masses times R. And so we can write a Lagrangian that involves, I think this is called a reduced mass. It's usually indicated as mu. So 1/2 mu times this coordinate r dot squared minus u of r, where this reduced mass, if that's the right name, is m1 times m2 over m1 plus m2. And what we've accomplished is to reduce a two-body problem to a one-body problem.